May this video soothe the fatigue of your long day. Take a moment to watch quietly, to listen in stillness, and may it bring you a peaceful dream tonight. What is the most extreme form of matter in the universe? Is it the explosion of a star or the very fabric of space-time being torn apart? Yet before total collapse, there is always a mysterious force defending the final boundary. Are you ready? Let's dive into the core of the universe's extremes. Inside stars, the accumulation of magnetic energy triggers massive solar flares, like a giant whip lashing out into the cold void of space. In a distant supergiant star, its core begins to fuse iron, igniting a chain reaction that eventually rips the star apart in a spectacular hypernova explosion. In the case of a rapidly spinning magnetar, internal pressure builds up until the crust fractures in what is known as a starquake, unleashing immensely powerful gamma-ray bursts. These are all examples of the universe reaching its critical points, moments when the balance of cosmic forces begins to break down. The matter that makes up planets, stars, galaxies, and even ourselves may appear stable, but it all walks a fine line of delicate balance. From the smallest atom to the largest supercluster, when anything is pushed past a certain threshold, chaos inevitably follows. Yet hope is not lost. Almost always, some form of subatomic safety net intervenes just in time to restore order and prevent absolute destruction, like Dr. Jekyll managing to suppress the darker instincts of Mr. Hyde. This balancing act is most vividly embodied by neutron stars, the universe's last bastion before total annihilation. These are perhaps the most extreme objects in all of spacetime, tiny yet unimaginably dense, dead stars spinning at phenomenal speeds, constantly defying the laws of physics. Their surface gravity is so powerful that mountains can only reach a few millimeters in height. Drop something from above, and it will reach half the speed of light before hitting the ground. And yet when we delve deeper into their interiors, through layer upon layer of increasing density, things only become more extreme. Hidden within their cores lie strange, exotic secrets, where matter is subjected to pressures found nowhere else in the universe. These conditions may even force us to rethink the very fundamentals of physics. Neutron stars are nature's ultimate physics laboratories, pushing ordinary matter to the brink of destruction. To understand their inner workings is to get closer to the true essence of reality itself. So where then lies the universe's ultimate limit? How far can we push before everything collapses? What, after all, are stars truly made of? On Christmas Eve of 2024, while humanity celebrated on Earth, the Parker Solar Probe was making history. Traveling at 200 kilometers per second, it soared through space, skimming just 6 million kilometers above the sun's blazing surface, the closest any man-made object has ever ventured to our star. 6 million kilometers may still sound far, but from this region, the corona, the sun's outermost layer, erupt tremendous solar storms called coronal mass ejections. These are like atomic bomb clouds made of subatomic particles the size of mountains. If they reach Earth and overwhelm our magnetic field, they could trigger widespread blackouts. One of the Parker probe's missions is to trace the source of this immense energy. Descending past the corona, we find the chromosphere, a thin layer with temperatures around 5,000 degrees Celsius. Below that lies the sun's visible surface, the photosphere. Constantly churning and bubbling, the photosphere is like the frothing lid of a cosmic cauldron, where superheated material surges upward in powerful convection currents. It's an awe-inspiring sight, but to truly grasp the sun's alien and volatile nature, and to understand what it might reveal about the hidden cores of neutron stars, we must rewind time more than a century, to a world where the Parker Solar Probe was not yet conceived. There was once a young scientist named Meghnad Saha, best remembered for his development of the Saha ionization equation. Thanks to his work, astronomers could estimate how much of the matter in different parts of the sun was ionized by measuring local temperature and pressure. This allowed them to determine the state of the sun's material. In physics, ionization is the process of stripping electrons from atoms, pushing matter to a critical point. In a simplified atomic model, negatively charged electrons orbit a positively charged nucleus. While not a perfect analogy, it's much like how planets revolve around the sun. A neutral atom's opposite charges balance each other, and this attraction keeps the electrons in orbit. But if energy, such as heat, is added, electrons may gain enough power to break free from this atomic bond. Electrons declare their independence. In the words of physicists, the matter becomes ionized. Physicists and astronomers use what's known as an equation of state to calculate this balance. It describes the intricate relationship between temperature, pressure, and density within the different layers of a star. A softer equation of state means the core is more easily compressed, while a harder one offers greater resistance to gravitational collapse. Keep this in mind. Equations of state are central to understanding the internal workings of neutron stars. Interestingly, even though astronomers cannot see or reach the solar core, they have developed highly precise models of its equation of state. One of the key tools in this research is an elusive subatomic particle, the neutrino. During hydrogen fusion in the core, the Sun produces an enormous number of neutrinos, about 1.79 pi 10 squarth every second. These neutrinos stream out of the Sun and spread throughout the solar system. Stretch your hand toward the Sun, and more neutrinos pass through your thumbnail in 1 second than the number of people on Earth. Over your lifetime, the number of neutrinos passing through your body is roughly equal to the number of stars in the observable universe. What's remarkable is that the number of neutrinos produced by the Sun is extremely sensitive to the core's conditions, especially its temperature. Even a slight change in the Sun's internal temperature causes a dramatic shift in neutrino output. That makes solar neutrinos the perfect thermometer for measuring the core's temperature, an astounding 15.7 million degrees Celsius. Understanding the Sun in this way is vitally important and has far-reaching consequences. The Sun is by far the closest star to us, 260,000 times closer than the next nearest star. While astronomers also study other stars using a method called asteroseismology, the level of detail we have for the Sun is unmatched. That makes it our benchmark for understanding all other stars in the universe. As such, the Sun and its equation of state serve as the ideal starting point for exploring how stellar states evolve, especially at the end of a star's life. Although the Sun may maintain hydrostatic equilibrium for billions of years, nothing in the universe lasts forever, not even stars. Eventually, the Sun will run out of fuel in its core, and the nuclear reactions will cease. It will be as if Mr. Hyde temporarily overpowers Dr. Jekyll. The result is a charged soup composed of electrons and atomic nuclei, known as plasma. In school, we are taught that matter exists in 3 states: solid, liquid, and gas. But in reality, there are more states than that. Plasma is just one of many exotic states we will encounter as we venture deeper into the core of a neutron star. The Saha ionization equation tells us that although the temperature of the Sun's photosphere is around 5,500 degrees Celsius, it's not high enough to strip every electron from its atom. Instead, the photosphere is only partially ionized, a mixture of hot gas and plasma. To find a region where plasma truly dominates, we must go deeper, into an area where the temperature reaches at least 10,000 degrees Celsius. When we reach about a quarter of the way into the Sun's interior, we arrive at its core. This is an environment of extreme density and pressure. The immense weight of all the outer layers presses down on the solar center with unimaginable force. Here, the pressure is 250 billion times greater than Earth's atmospheric pressure. Plasma is so tightly compressed that its density rises to 150 grams per cubic centimeter, nearly 8 times denser than gold. Although the core is primarily composed of ionized hydrogen, the lightest element in the universe, a single spoonful of this material would weigh as much as a baby. If you filled an Olympic-sized swimming pool with solar core matter, it would outweigh all the passengers and cargo of a large airplane. If gravity had its way, the solar core would collapse under such immense pressure. But it doesn't. Instead, the Sun remains stable, continuing to operate for billions of years, walking a tightrope of balance from within. What prevents the Sun from crossing its critical point? In the core, hydrogen atoms are compressed so tightly that they undergo fusion. Every second, about 620 million tons of hydrogen are converted into 616 million tons of helium. The missing mass is transformed into energy. This means the Sun produces an equivalent of 4 million tons of energy in the form of light every second. Yet the Sun is so dense, that it takes these photons an average of 170,000 years to reach the surface. The outward pressure generated by this nuclear fusion, combined with the intense heat of the core, is the only thing preventing the Sun from collapsing under its own gravity. This delicate balance between outward pressure and inward gravitational pull is called hydrostatic equilibrium. What follows will be nothing short of spectacular. And in some stars, these final acts of destruction will lead to the birth of something truly bizarre. Physicist Ralph Fowler, originally trained as a mathematician, later shifted his focus to physics due to the influence of personal experiences. He went on to make profoundly important contributions to theoretical astrophysics. A Nobel Prize was eventually awarded for a discovery that, without the foundational work of Ralph Fowler, would not have been possible. That discovery showed that one of the many critical thresholds in stellar evolution could actually be surpassed, placing the particles that make up a star onto an entirely new and more perilous subatomic tightrope of balance. The discoveries of Fowler and Subramanian Chandrasekhar both centered around revealing the internal mechanics of a special type of star. If you look up into the winter night sky from the northern hemisphere, one particular star immediately stands out. It is not only the brightest, but also flickers vividly in various brilliant colors. Sirius, the alpha star of the constellation Canis Major. It has held significant cultural influence throughout human history. After late July, Sirius begins to rise and set with the Sun, temporarily vanishing from the night sky. But Sirius is not a lone wolf. It has a companion star, often called the pup star. The two orbit each other once every half-century. In the years following World War I, the true nature of the pup star puzzled astronomers. On one hand, it was smaller than Earth, but somehow hotter than the Sun. In 1922, astronomer Willem Jacob Leyden gave these strange objects a name: white dwarfs. What exactly are white dwarfs made of? One thing is clear. To pack a sun's worth of mass into a space the size of a planet, a white dwarf must be extraordinarily dense, about 1 billion kilograms per cubic meter. A single cubic centimeter of white dwarf matter weighs as much as an elephant. A container full of it would match the mass of the Great Pyramid of Giza. Logically, something so dense should collapse. In the Sun, it's the outward thermal pressure that counteracts inward gravitational force. But in the far denser environment of a white dwarf, this pressure alone isn't enough to support the star. So what prevents a white dwarf from collapsing under its own gravity? Ralph Fowler, along with Arthur Milne and the legendary astronomer Arthur Eddington, provided the answer. The material inside a white dwarf is in a state known as degeneracy, a cutting-edge concept in the 1920s. That decade is most famous for jazz, flappers, prohibition, and speakeasies, but it was also a fertile period for the rise of new physics. Physicists were striving to understand a revolutionary science, quantum mechanics. This was the era of Schrödinger, Heisenberg, Bohr, and Pauli. It was Pauli's exclusion principle that lay at the heart of degenerate matter and revealed what white dwarfs and later neutron stars are truly made of. Why is it called quantum mechanics? Because in the atomic world, only specific quantities are allowed. For example, subatomic particles can only possess discrete energy levels, and particles with the same energy must differ in some other property to ensure no two particles are exactly identical. These alternative attributes are limited in number, meaning the space available at each energy level is also limited. To visualize this, imagine a skyscraper where each floor represents an allowed energy level in the quantum world. Like a real skyscraper, each floor has a legal occupancy limit. Once full, no new occupants can enter that level. That's why it's called the exclusion principle. In the Sun, particles are sparse enough that the maximum capacity of each level is never reached. But when matter is compressed to the extreme densities found in white dwarfs, everything changes. The lowest energy levels fill quickly, followed by the next and the next. This resistance to further compression is known as degeneracy pressure. That was Fowler's great contribution, one that, nearly a century later, still doesn't receive the widespread recognition it deserves. His early death likely prevented him from receiving the Nobel Prize he merited. Today, we know that when a star like the Sun dies, about half its mass is compressed into an incredibly dense white dwarf. The other half is ejected, like a snake shedding its skin, expanding into a beautiful and complex cloud known as a planetary nebula. And that, in roughly 7 billion years, is the fate that awaits our own sun. However, for the most massive stars, an entirely different fate awaits. Let's return to the night sky. If you begin at Sirius and move upward and slightly to the right, you'll quickly come across the famous 3 stars that make up Orion's belt. Following that same line further, you'll encounter a group of stars shaped like the letter Celsius. You've now arrived at the Hyades cluster, which represents the head of Taurus, the bull. Its horns extend from the tips of the V, and at the end of the left horn, near the star Alnath, sits the Crab Nebula, one of the most iconic clouds of gas and dust in the sky. The Crab Nebula is a supernova remnant, the ruins of a once mighty star that has burned through its fuel. In 1054 AD, Chinese astronomers recorded the appearance of a new star in the sky, a guest star, so bright that it remained visible even during the day for nearly a month, and it took 2 full years to fade from the night sky. To describe these events as merely super is a vast understatement. In just a few seconds, a supernova explosion releases more energy than the sun will emit over its entire multi-billion-year lifetime. And they're not especially rare. It's estimated that a supernova explodes somewhere in the universe every 10 seconds. That means over 100 have gone off since you started watching this video. However, what lies at the center of the Crab Nebula is perhaps even more astonishing: a neutron star. If the density of a white dwarf is already hard to comprehend, a neutron star is 100 million times denser. Just a single spoonful of neutron star matter would weigh more than the total mass of all 108 billion humans who have ever lived. While white dwarfs are roughly Earth-sized, neutron stars are much smaller, closer in size to a city. The neutron star at the heart of the Crab Nebula has a diameter of just 21 kilometers, making it roughly the size of London, and much narrower than Tokyo. More than a solar mass of matter is crammed into that unimaginable space. The gravity of a neutron star is colossal. Escaping Earth's gravity requires a speed of about 11 kilometers per second. To escape a neutron star, you'd need to travel at 150,000 kilometers per second, around half the speed of light. On Earth, gravity is weak enough to allow mountains like Everest to rise nearly 9 kilometers high. But on a neutron star, the tallest mountains are less than a millimeter tall, making them some of the smoothest objects in the universe. They also spin at dizzying speeds. The neutron star in the Crab Nebula rotates 30 times per second, and the fastest known ones can spin hundreds of times each second. When the original star exploded in a supernova, not only was its mass compressed, so was its magnetic field. A typical neutron star's magnetic field is 100 billion times stronger than a refrigerator magnet. This field often confines intense beams of radiation that stream out from the star's poles. When Earth crosses these beams, we detect them as a series of regular pulses, hence the name pulsar, a combination of pulsating and star. Chandrasekhar's great discovery was that Fowler's degeneracy pressure can only support white dwarfs up to a mass of 1.4 times that of the Sun. If a dying star's core exceeds this limit, it's another victory for Mr. Hyde over Dr. Jekyll. The ensuing collapse forces electrons and protons to merge into neutrons, and a neutron star is born. But neutrons, like electrons, obey the Pauli exclusion principle. No 2 neutrons can share exactly the same quantum state. This means that each energy level has a finite capacity, and once filled, even gravity cannot compress the star further. This neutron degeneracy pressure provides the final defense against total collapse. It's the only thing keeping the neutron star balanced at the very edge, just a few dozen kilometers from complete destruction. From the name alone, one might think these mysterious objects are made entirely of neutrons, but they're not. The deeper you go into their structure, the stranger the material becomes. Just like our sun, whose surface barely hints at its inner extremity, our journey to understand the true interior of neutron stars has only just begun. And one of the biggest recent clues came from a neutron star that, by all rights, shouldn't even exist. With the help of an X-ray telescope mounted on the International Space Station, NICER, the Neutron Star Interior Composition Explorer, we now have a vital tool for probing the structure and composition of these dense, mysterious objects. Through its observations, Neutron Star Interior Composition Explorer has begun to unveil the mysteries of the physical states deep within neutron stars, offering tantalizing clues. To fully grasp NICER's discoveries, we must understand the layered structure of a neutron star, from surface to core. Suspended just above the surface is a thin atmosphere, only about 10 centimeters thick, composed of hydrogen and ammonia. Its density rivals that of diamond, and it's superheated to around 2 million degrees Celsius. Beneath this lies the crust, where the pressure is so immense that electrons are stripped from atomic nuclei, leaving behind an ionized sea of electrons, protons, and neutrons. Within this crust, enormous forces distort and mold protons and neutrons into bizarre structures found nowhere else in the universe. Physicists call this form of matter nuclear pasta, a theoretical substance predicted by detailed computer simulations under extreme pressure. If nuclear pasta truly exists, it would be the strongest material in the universe, about 10 billion times stronger than steel. According to these simulations, nuclear pasta exists in several forms, each named after a type of Italian pasta. Near the surface, protons and neutrons form bubble-like structures nicknamed gnocchi. As pressure increases deeper within, these gnocchi are flattened into spaghetti-like shapes. Deeper still, the matter compresses into sheet-like forms, dubbed lasagna. Collectively, the nuclear pasta layers are only about 100 meters thick, yet they weigh more than 3,000 Earths. For a long time, astronomers believed they had a good grasp of neutron star structure. But in 2019, the universe threw them a curveball. The most massive neutron stars should logically be the smallest. Greater mass means stronger gravity, which should compress the star into a smaller volume. However, when astronomers used NICER to observe a neutron star named J740+6620, that expectation was shattered. They quickly realized that this was one of the most massive neutron stars ever discovered, slightly more than twice the mass of our Sun. Therefore, it should have been among the smallest, but its size was comparable to that of another neutron star with just 2/3 of its mass. J740+6620 became the center of intense debate. How could such a massive star be so large? One possibility was that astronomers had been using the wrong equation of state. Unlike the Sun, determining the correct equation of state for neutron stars is vastly more complicated. Hundreds of theoretical models exist, and obtaining detailed observational data is extremely difficult. Earth's laboratories cannot replicate the extreme pressures and temperatures inside neutron stars. J0740 might help narrow down the possibilities, especially because its large size implies that its interior may be less compressible than previously thought. In astrophysical terms, less soft. But another more intriguing explanation is that this unexpected stiffness could originate from even deeper within, beneath the layers of nuclear pasta, at the very core. Before J0740 challenged expectations, the prevailing view was that a neutron star's core might consist of a quark soup. Protons and neutrons are not fundamental particles. They are made of 3 quarks each. The idea was that, under extreme pressure, protons and neutrons would be crushed and broken apart into their constituent quarks. But breaking the strong nuclear force that holds quarks together requires immense energy. Energy that could otherwise be used to resist gravitational collapse. That's why more massive neutron stars were expected to be smaller, because more energy would be diverted to disassembling particles. But as we've seen with J0740, that isn't always the case. This raises further questions about strange particles called hyperons. There are 6 types of quarks. Protons and neutrons contain just 2, up and down quarks. The other 4 are the top, bottom, strange, and charm quarks. Hyperons are particles that contain strange quarks, but not top, bottom, or charm. They were first detected in cosmic ray experiments during the 1940s, but they decay almost instantly, making them difficult to study in detail. Some popular models of neutron stars suggest that their cores could reach such extreme temperatures and pressures that not only are hyperons created, but they remain stable for extended periods. However, there's a catch. The presence of hyperons should soften the equation of state, reducing the star's ability to resist gravity. This would make the interior of the neutron star softer, not harder. After the discovery of J0740 plus 6620, the idea that neutron star cores are made of quark soup or include strange quark-containing hyperons suddenly became far less tenable. But if the quark soup model is eventually discarded, what does that mean? And if further research continues to cast doubt on it, what could be lurking deep inside the core of a neutron star? One factor often overlooked in quark soup models is dark matter. Since the 1930s, astronomers have found that extra gravitational pull is needed to explain many observations, such as galaxies rotating too quickly or bending light more than expected. One explanation is that the universe is filled with invisible material acting as gravitational glue. The term dark matter was first coined by Swiss-American astronomer Fritz Zwicky in a 1933 paper. Remarkably, just a year later, he and Walter Baade were also the first to propose the existence of neutron stars. If dark matter truly exists, then massive stars moving through space would frequently pass through it, gradually accreting some of it. This dark matter would then sink into their cores. After such a star explodes in a supernova and becomes a neutron star, the dark matter would remain trapped inside. Studies suggest that adding dark matter to the quark soup could stiffen the equation of state, giving the star greater resistance to gravitational collapse. This may explain why J740 isn't as small as initially predicted. But this is only a moderate tweak to the quark soup idea. There's another theory that completely abandons it. That theory also has its roots in early 20th century India, and in a man who once worked at the University of Calcutta alongside Meghnad Saha. His name was Satyendra Nath Bose. Born on New Year's Day in 1894, Bose was a self-described perfectionist with a fondness for the poetry of Tennyson. He could have chosen many fields of study but chose science, believing it was the key to his country's future prosperity. He earned one of just 32 coveted spots out of 2,000 applicants at Presidency College in Calcutta, the best place in India to study science. A few years later, Bose began collaborating with Saha. Together, they translated Albert Einstein's papers on relativity from German into English, so Indian students could read them more easily. In 1924, Bose moved to Dhaka, Saha's hometown in East Bengal. That same year, Saha visited him, and their conversation inspired Bose to develop new ideas about the behavior of certain subatomic particles. Struggling to publish his ideas in English-language journals, Bose took a bold step. He wrote directly to Einstein. It was a daring move, and it paid off. Einstein was so impressed with Bose's ideas that he translated the paper into German himself and submitted it to a leading academic journal. Their collaboration led to what is now known as Bose-Einstein statistics, and quickly predicted the existence of an entirely new state of matter, the Bose-Einstein condensate. Today, physicists classify subatomic particles into two camps: bosons like the photon, and fermions, like the proton and electron, named after Italian-American physicist Enrico Fermi. The key difference lies in a property called spin. Bosons always have whole number spin values, while fermions have half-integer spins, like in half. Crucially, spin also has a direction, most commonly described as up or down. The Pauli exclusion principle, which we've encountered before, applies strictly to fermions. Two protons or neutrons cannot occupy the same quantum state at the same time, in the same place, with the same spin. Bosons, on the other hand, behave quite differently. In a Bose-Einstein condensate, all bosons move together at the same speed, acting like a single giant quantum particle. If bosons in a neutron star core were to pair up with aligned spins, they might harden the equation of state and provide outward pressure against gravity, a new safety net preventing Mr. Hyde from breaking through the door. This idea has led some astronomers to suggest that the most massive neutron stars, those with at least twice the mass of the Sun, like J74, might in fact be Bose-Einstein condensate stars. Regardless of its composition, J0740 plus 6620 remains one of the most massive neutron stars ever discovered. But that raises a profound question. How massive can a neutron star truly be? And what happens if that mass is ever exceeded? Is there another safety net to catch it? Physicist George Volkoff, along with Robert Oppenheimer and Richard Tolman, conducted important early research on neutron stars. They jointly calculated the maximum mass a neutron star could possibly have, a limit now known as the Tolman-Oppenheimer-Volkoff limit. Their initial result placed this upper boundary at only 70% of the Sun's mass, significantly lower than the Chandrasekhar limit for white dwarfs. However, later studies proved this to be a severe underestimation. With improved understanding of the equation of state for neutron stars during the 1990s and advances in computation, astronomers substantially revised the TOV limit. It is now believed to range between 2.2 and 2.9 times the mass of the Sun. Yet to narrow this range further, a thoroughly modernized technique would be necessary. In the summer of 2017, the astronomy world was abuzz with speculation. It started when astronomer Craig Wheeler posted a mysteriously worded tweet on August 18th. New LIGO source with optical counterpart. Blows your socks off. Internet sleuths searched through public observation logs of major telescopes and found several had urgently been redirected toward the same galaxy, 140 million light-years away. 2 months later, astronomers finally revealed what had happened. Just a day before Wheeler's tweet, LIGO had captured a historic signal. 2 neutron stars had collided in NGC 4993, unleashing a cataclysmic event. 70 observatories across 7 continents and in space recorded the aftermath of this collision. For LIGO, the detection was akin to how swimmers, boats, and dolphins generate ripples in water. Massive objects moving through space distort space-time itself, creating gravitational waves. These waves are ripples in the very fabric of space-time. This was the first time astronomers had detected gravitational waves from a neutron star collision. As the 2 stars spiraled inward and collided, the amplitude and frequency of the waves spiked dramatically. By carefully analyzing the data, astronomers could eliminate equations of state that didn't match the observed waves, allowing them to constrain the TOV limit to between 2.1 and 2.17 solar masses. Still, this is far from definitive. On one hand, the heaviest known neutron star to date, PSR J9520607, weighs in at 2.35 solar masses, seemingly exceeding the proposed TOV limit. As always, the details matter. The simplest TOV limit applies only to non-rotating neutron stars. Most neutron stars, however, do rotate, which can slightly raise the limit. But what happens when neutron stars collide? The combined mass of the 2 stars involved in the 2017 event was 2.8 solar masses, clearly exceeding the TOV limit. So, what happens when a neutron star crosses this boundary? When the total mass exceeds the TOV limit, not even degeneracy pressure, the eternal tug-of-war between Jekyll and Hyde inside each star, can serve as a strong enough safety net. What happens next? Is there yet another level of density before complete annihilation? This remains a fiercely debated topic, with only 2 realistic possibilities. One option is that the neutrons are squeezed so tightly they dissolve into a sea of quarks, forming a quark star. Calculations suggest that objects composed of strange quarks are the most likely to be stable, so these hypothetical stars are sometimes called strange stars. Fittingly, strange stars may exhibit some truly bizarre properties. If 2 quark stars were to collide, they might generate quark nuggets, also known as strangelets. These clumps of strange quark matter, weighing between 100 grams and 100 kilograms, would be astronomical zombies, converting anything they touch into more strange matter. At one time, quark nuggets were even considered candidates for the universe's elusive dark matter. Although astronomers have never directly observed a quark star or quark nugget, there are ways that their existence could be revealed. Experiments such as the Ice Cube Neutrino Observatory, buried deep in the Antarctic permafrost, might be able to detect the subatomic debris created when a quark nugget crashes into Earth's upper atmosphere. However, if the colliding neutron stars do not collapse into a quark star, then only one possibility remains: a black hole. When gravity pushes past the final critical point of a star's resistance, what you get is a black hole. Dr. Jekyll no longer has any way of keeping Mr. Hyde in check. Ultimately, collapse is inevitable. The star's core contracts entirely until all matter is compressed into a point of infinite density, known as a singularity. It is precisely here that the laws of physics break down. Space and time cease to exist, and with them, our ability to describe what is happening vanishes. At least, that's the case according to Einstein's general relativity. But general relativity is not the only theory. As we've seen, it was quantum mechanics that so elegantly explained how white dwarfs and neutron stars manage to teeter on the brink of destruction. You can't just throw that theory out the window after a neutron star collision. The problem is, general relativity and quantum mechanics are notoriously incompatible. Their descriptions of the universe are fundamentally at odds. They cannot both be completely right. Most likely, one, or perhaps both, are merely approximations of a deeper, more complex theory of quantum gravity. So, in this cosmic game of chicken, which theory is more likely to blink first? Interestingly, neutron stars might just hold the answer. The 2017 collision event, known as GW170817, was the first time astronomers observed both gravitational waves and light signals from the same celestial event. Detecting more than one type of signal from a single event is known as multi-messenger astronomy, and GW70817 arguably marked its modern debut as a mature scientific tool. Just 2 seconds after the gravitational waves from GW70817 reached Earth, astronomers detected a dazzling gamma-ray burst from the same region of the sky. The time difference between the two signals allowed scientists to measure how fast gravitational waves travel. The 2-second gap matched the predictions of general relativity, while conflicting with several alternative theories of gravity, thus helping to rule them out.